Okay, in our last video, we looked at how to prepare enols and enolates. And we said that these enols are pretty easy to prepare by using catalytic acid or base. So let's make a note here. So catalytic acid or base can be used to make these. And if we think about our enolates, we said that in order to form an enolate, you must use a really, really strong base, meaning we can't just throw generic hydroxide at most ketones and get a substantial amount of our enolate. So with these, we typically make these with strong bases. All right, so what I wanted to do is I wanted to do a little bit of review over what qualifies as a strong enough base, right? Because sometimes we're in this gray area where it's like, well, is it strong enough? Well, maybe we sometimes have to look at pKa values too. So let's do a little bit of review, and we'll just say selecting a base for enolate formation. And like I said, anytime you see this ATE suffix, that's the one where we have the negative charge. So in the example above, you can see that negative charge is delocalized across the oxygen and carbon. And we need to usually use a strong base. Because we want to be able to trap that enolate. So let's take a look at some examples, and we'll do some practice. And let's just say we've got acetone, one of the simplest ketones. We've got an alpha position right there, and we've got 3 protons. Well, I went ahead and I looked at the pKa table, and the pKa table by Dave Evans says that the pKa of those protons is about 19.2. And we know that we're going to react it with some sort of base, so I'm just going to call this B-. And this is going to act as the acid, meaning it's going to be the proton donor, and this is going to be the base. And in this reaction, the hope is that our base will grab one of these protons and form our enolate. And you can show your enolate in either form, right? So you can show it with the negative charge on that carbon or on the oxygen. I really have no preference because they're the same thing. So we've got our enolate. And our conjugate acid would just be HB. So this would be our conjugate base. And this would be our conjugate acid. All right, if you remember way back to first term organic chemistry, I showed you a hint. And I said really what you have in solution are 2 acids. You've got your conjugate acid and your original acid, right? In this case, we want the pKa of our original acid, meaning this acid over here, to be about 5 or more pKa units lower. So let's make a note. Should be greater than 5 pKa, actually greater or equal to 5 pKa units lower than the pKa of your conjugate acid. And by doing that, this reaction arrow essentially is no longer under equilibrium conditions, right? Meaning we're pushing the reaction all the way to completion. All right, so if we go through our acid and base sheets, we can try to find an appropriate base that will work for that. But let's do a few examples first, and then we'll come back to that one. So let's take this example where we have the diketone. And this was one I used in the last video. And we said in this diketone, these alpha protons in the middle are going to be the most acidic, because if you were to pluck one off, it could resonance, or the negative charge could resonance delocalize to either carbon, right? And if you look this up in the pKa table, it's going to have a pKa of about 9. So this is going to act as our acid. And then we need some sort of base. And I'm just going to put a question mark here. We'll try to figure out what that is. And our goal is to get this to go all the way to our enolate. And like we said, this tends to form a lot more readily because we've extended conjugation, and it's more stable because we have more resonance delocalization. And then the conjugate acid we'll put over here. So this would be our conjugate base, and this would be our conjugate acid. All right, so if we think about this, right, up here, if we scroll up, I said that the pKa of our conjugate acid should be 5 higher, or conversely, the pKa of our original acid should be 5 lower at a minimum. All right, so if we think about this, it should have a pKa that is greater than or equal to 14 for our conjugate acid. All right, so then we could start looking around and we could say, well, what conjugate acids of generic bases have a pKa of greater than 14? Well, the one that seems to make the most sense here would be hydroxide, because we know that water, being the conjugate acid, has a pKa of about 15. So in this case, the reaction is going to push itself almost entirely to completion. It's not going to be in equilibrium anymore, and we're going to get nearly 100% of our enolate, which in this case is our conjugate base. All right, so let's think about this example again up here. Well, in this case, if we think about the conjugate acid that we had here, this should have a pKa that is greater than or equal to, what would that be? It'd be about 25-ish. So we need to find a base where the resulting conjugate acid is quite high. And in this case, I'll show you the base that's most commonly used. It's a kind of special base. It's a little harder to deal with than a hydroxide, that's for sure. But it has a nitrogen with a negative charge. And it's got these isopropyl groups dangling off of it. And then the counter cation is lithium. So lithium's got that positive charge. So in this case, when we look at this, we still have these alpha carbons right here. And we still have 3 protons coming off of them. I'm going to kind of slide this over, give me some more room. And this is going to be my acid. And we said that this acid has a pKa of 19.2. And this is going to be our base. And this is a really strong base, and we'll see why in a second. But when this reacts, we're going to form our enolate at nearly 100%. And then our conjugate acid is just going to be that nitrogen with its proton back. So this would be our conjugate base, and this would be our conjugate acid. And if you look up the pKa of this amine, it's going to be in the range of about 36 to 38. So as you can see, it's definitely more than 5 pKa units larger than this original acid, so that's good. But there's also another cool feature with this. If you look at this reagent, it is a good base, but terrible nucleophile. Which is good for a lot of these reactions because we don't want our base to do any unwanted nucleophilic chemistry. And so in our quiz, I'll ask you, why is this a bad nucleophile? But as you can probably imagine, there's something going on here that's not going to allow it to attack an electrophile as easily. This base is called lithium diisopropyl amide. Most people just call this LDA. It's a lot easier to write out, and it's going to be a base that we use a lot of in this enol and enolate chapter because it's so strong and it's a terrible nucleophile. However, if you've got some of these starting materials where you get a lot of extended conjugation, you don't even need to use a exotic, expensive, hard to handle base. Sometimes hydroxide gets the job done. All right, good luck studying.